So welcome back everyone to MathXplore Infinity. I'm absolutely thrilled to have you join me once again. So today we are going to delve into a fascinating concept in mathematics known as mollifiers. But before we dive into the intricacies of the mathematics involved, let's sustain our tradition by starting with a relatable analogy, right? With a motivation to make this concept, more accessible even to non-mathematicians. Imagine yourself driving on a bumpy, rough road, right? That is challenging to navigate. In the realm of mathematics, this uneven road would represent a function that actually lacks smoothness, right? Function characterized by discontinuities or sharp irregularities, right? You can think of step functions, for instance. So now consider a solution to this, to our rather unpleasant driving experience, right? Which will typically be a road roller, right? A robust machine capable of smoothing out the rugged road surface, right? Making it significantly more comfortable to traverse. So in the world of mathematics, we have a similar tool, right, known as mollifiers, right? Much like the road roller's role in transforming the uneven road, modifiers actually serve as smoothing agents, right? They are designed to specifically refine and smooth out rough mathematical functions. So, how does this transformation actually take place? Actually, how does how does the modifier actually work its magic, right? Turning a mathematically challenging or jack function into something more manageable. The answer actually lies in the concept of convolution, right? A topic that we have explored in a previous video. If you're curious to delve deeper into the mechanics of convolution, um, I highly recommend checking out my previous video on convolution and regularization, right? Because I believe it's actually a valuable resource that will provide you with a more in-depth understanding of this crucial concept. Convolution in essence it's a precise mathematical operation, right, that combines the rough function with the modifier, right? You can visualize it as a meticulous process, right, where the road roller glides over the uneven road surface, right, and effectively erasing every bump and potholes. So in a similar fashion, right, convolution addresses the irregularities, right, within the mathematical function. So as a consequence of this convolution operation, right, the typical end result is usually a mathematically smooth function, right, much like a freshly paved road. So now let's get into the mathematics per se, right? So the most interesting part. So we start with a definition. So definition. Definition. So a sequence of modifiers say we call it rho n greater equal than 1, right? The sequence of modifiers is we change the column, is any sequence, right? It's any sequence of functions defined on Rn, right? On Rn such that these properties, the following properties hold. Rho n, is infinitely continuously differentiable with compact support. let me hide this C properly. Good. The support of rho n is actually contained into the closed unit ball of radius 1 over n. I mean the integral over Rn of rho n of x dx should be 1, right? And rho n is positive, a positive function, right, on Rn. Of course, this holds for every n, right, greater or equal than 1. Okay, so this couple of properties should hold for us to have a sequence of mollifiers. So in what follows, we will systematically use the notation rho n to denote a sequence of mollifiers. So however, note that it is actually it is easy to generate a sequence of mollifiers starting with a single function, function that we will call rho, right, which is C infinity C infinity continuously differentiable with compact support, right, such that well, the support of rho is contained into the closed unit ball, right? I mean rho is greater or equal than 0 on Rn, and rho does not vanish identically. So this is different from 0. Looks ugly. Quite better. Okay, so for example, just give a example of such a function. So for example, the function defined by put it in color, defined by rho of x equals exponential of 1 over, put norm of x here, right, squared minus 1 if norm of x is strictly less than 1 and 0 else. Right, I mean you can actually check that this function, what you can check. You can check that I mean this function actually satisfies the above property, right? But this is actually infinity of and the support. And I think it is obvious that the support is contained into the closed unit ball, right? And also that rho is greater or equal than 0. Okay, good. So we obtain a sequence out of this function. We obtain a sequence of mollifiers, right, by letting rho n of x to be c times, we'll tell you what c is, n to the power n, right, times rho of nx, right? I mean observe that this capital N is exactly the dimension of of Rn, right? So, and C is, it's just a normalizing factor. So, with C being equals to 1 over the integral over Rn of rho of x dx. Okay, good. So, just for, for visualization purpose, so let me just try to draw how the function rho could look like. So let's say here we have -1, and here we have 1. So of course this is the origin. So we typically have something like this, right? So this is the bell curve, right? For those who have knowledge in statistics, you know that this is kind of a normal distribution. Okay, so let's state our first proposition for this lecture. So proposition 4.21. Of course, this is in continuation with, in accordance with, with our lecture series, right, that we started so far since the beginning. So, assume f is a continuous function on Rn, right? Then put it in color. Then rho n convoluted with f, right, converges to f, right, as n goes to plus infinity uniformly. Uniformly on compact set of Rn, right? Just for your recall, if you don't know what uniform convergence on compact set is, this means that for every k, right, containing to Rn, right, k compact, the convolution product of these two functions, right, restricted to k, actually goes to converges to f restricted to k. Okay, so let's go into the proof. Well, let k, right, be a fixed compact set. Right. So given epsilon positive, right? So by continuity of f on Rn, right? So we know that there exists a delta positive, right? That obviously, depending on the delta actually depends on the compact set k and epsilon, right? So there is a delta positive such that the absolute value of f of x minus y minus f of y, right, is actually slightly less than epsilon for every x in the compact set k, and for every y in the ball, provided that y is actually in the ball centered around 0 and radius delta. This is just typically by definition of continuity of the function f, right? Okay, so we have for every x in Rn that the convolution product. So this is rho n convoluted with x, with f applied to x, minus f of x, right? This is equal to the integral. This is just by definition, the integral over Rn of, I think I'll go step by step here, of rho n of x times minus y, sorry, times f of y dy, right, minus f of x. So this is again equals to the integral over Rn of, I think here I will go a bit faster. So this is the integral of f of x minus y, right, minus f of x times rho n of y dy. Well, so let me just tell you how this equality emerges. So observe that, note that the integral over rho n is 1, right? Because rho n, as I said at the beginning, is actually stand for sequence of modifiers, so they integrate to 1, and then you also proceed by a change of variable. Okay. So well, if it is still not clear, observe that because the integral of rho n equals 1, so I can actually replace this f of x here by the integral of can replace this by the integral over Rn of rho n of y f of x dy. I think it's not visible. Let me just try to drag it a bit. Good. So this will be this again, right, dy. So and then prepare for a change of variable. Okay, so so this now is equal to, we know that rho n are supported in the closed unit ball, so this is the integral over ball, right, of f of x minus y minus f of x rho n of y dy. Now for this ball actually containing 2, because y actually varies, and I'll just show you something. So you are integrating over y, right, for y being in this ball. Okay, so for this ball containing 2 this, right, so that means for n strictly greater than 1 over delta, right, and x into k, right, we obtain, let me put the 4 here, so we obtain that the absolute value of rho n convoluted with f applied to x minus f of x, right, is actually less or equal than epsilon times the integral over rho n, right? Maybe I write everything right, of integral over Rn of rho n of cy dy, right? So this is exactly epsilon, right? But how is that, right? Remember that we prove here that, you saw that by continuity of the function f, this was actually less than epsilon, right? Provided that y is actually in the ball centered around 0 and radius delta, and also for every x in k. So if this condition holds here, right, this means, under this condition, this term, I can bound this term by epsilon, right? So once you fit out, so this, we get this. Okay, so think now we are done. So hence we have that, this convolution product actually converges to F, right, uniformly on compact. So and then we are done. Okay, good. So now let's state first theorem of this lecture. So this is theorem 4.22. So assume f is actually in LP of Rn, right? It's a p-integrable function. So let me just write this. Good. With, of course, p between 1 and infinity, right? Strictly less than infinity. Then rho n convoluted, the modifier convoluted, the sequence of modifiers convoluted with f actually converges to f, right, strongly in LP. Strongly in LP of Rn. So we have strong convergence and non-convergence. Okay, proof. So of course let f, right, be in LP of Rn, right, with, of course, p between 1 and plus infinity. So given epsilon positive, right, it follows from I think was theorem 4.12, right? Let me just highlight that. I strongly invite you once again to watch the video on convolution and regularization. This is where we investigated theorem 4.12, right? So this theorem basically stated that this space, the space of continuous function with compact support lies dense in L1. I think it was probably in the lecture about measure theory and integration. I don't remember, but please check out our previous videos. Okay, so this means the space of continuous function with compact support actually lies dense in L1 of Rn. So given epsilon positive, right, so it follows from theorem 4.12 that there exists say f1, right, in L, not in L1, but in CC of Rn, right, such that I think we will have to be more clear. This even dense to in LP of Rn, right, for p between 1 and plus infinity not included, of course. Okay, so there is this f1 in the space of continuous function with compact support such that the norm of f minus f1 in the LP norm, right, is actually strictly less than epsilon. Now, since f1, right, is actually continuous function with compact support, right, which is actually contained to the space of continuous function of Rn, right, it follows from our first proposition in this lecture. So it follows by proposition 4.21. This was our first proposition in this lecture. So it follows that rho n, right, convoluted with f1, right, actually converges to f1 uniformly on compact. Uniformly on every compact set of Rn. Good. On the other hand, you have by proposition 4.18, right? And please check out my previous video about convolution and regularization once again. So it follows by proposition 4.18 that we saw that the support of the convolution product, right, is contained into the sum of the closure of the sum of the essential support of each function, support of f1. So closure of this, right? So now we know that the support of rho n is actually contained into the closed unit ball, right? This is by definition of a sequence of modifiers. So this is contained into this plus support of f1. So let's put closure again. But we can actually remove closure because this is actually closed, right? This is also closed, so the sum is closed. So this is contained into this closure here plus support of f1. Okay. Now observe that this is actually compact, right? This is by Hein-Borel, right? Closed and bounded, right? And this is actually also, remember f1, f1 is continuous, so we saw that the definition, the essential support actually coincides with the usual definition of the support that we know, right? So the support of f1 here is actually also compact, right? Because f1 has compact support. F1 belongs to the space of continuous function with compact support, so this is compact. So you can even see it as compact as being a closed subset, right, of a compact set, right? Because f1 is in CC of Rn, so which means that there exists K compact, right? So there is this K compact subset of Rn such that the support of f1 is contained to K, but support of f1 is actually closed. So we know that every closed subset of a compact set is actually compact. Okay, so this means that the support of the convolution product here of rho n with f1 is compact, right? So it follows that the norm of rho n convoluted with rho 1 minus f1, like the LP norm of this, actually goes to 0, as n actually goes to plus infinity, right? this was a bit fast. So this is basically because the LP norm of this is just ON convoluted with f1 of x, right, minus f of x, everything raised to the power p dx. This is the p norm, the LP norm here, because I'm not going to write everything to the power 1 over p. So this is equals exactly to the integral over the support, right, of the convolution product, this with f1, right, up to the value of this minus f1 of x to the power p dx, right? But we know that this actually, on this, because this is compact, right? And we know that ON convoluted with f1 converges to f1 uniformly on compact, and then we saw that this is actually compact. So this whole thing here will go actually to 0. Okay, so finally, we write ON convoluted with f minus f, right, equals to this is just we include things that we know and then we remove. So this is ON convoluted. Oops, let me just. So this is ON convoluted with f1 minus f1 f minus f1. Sorry, right, plus this ON convoluted with f1 minus f1, right, plus finally f1 minus f, right. So and this, the LP norm of ON convoluted with f minus f, right, by triangle inequality, of course, this is less or equal than the LP norm of ON convoluted with f minus f1, right, the LP norm of this, plus the LP norm of ON convoluted with f1. This is basically by triangle inequality, right? So there's nothing hidden behind this thing. Okay, good. Now observe that this is actually, ON is actually in C infinity C of Rn, right? And f minus f1, right, is actually this is an element of LP, right? And observe that the space of C infinity C of omega of Rn, right, is actually contained into L1, right? So we can actually apply Young's inequality to say that this is actually less or equal. When you apply Young's inequality to the first term, right? The first term, so you get that this is less or equal than the one norm of ON, right, times the LP norm of f1 minus f. Right, now just write the other expression. Plus the norm of f1 minus f in LP norm. So again, this is actually by I think it was theorem 4.15. This was Young's inequality. So check out my previous video once again on convolution and regularization. It will be very useful and beneficial to you. So, but you know that the L1 norm of this is exactly 1, so this is actually less or equal than 2 times the norm of f1 minus f the LP norm of that, right? First, the LP norm of rho n convoluted with f1 minus f1. So, but of course, we saw that this actually goes to 0, right? And this was actually less than epsilon. Okay, so we conclude that well, the lim sup of norm of rho n convoluted with f minus f, the LP norm of this, right, is actually less or equal than 2 epsilon for every epsilon positive, like this is of, and therefore the limit of norm of rho n convoluted with f minus f is equal to 0. So with this, when we are done, good. Now let's kind of characterize dense subset of LP spaces. So corollary 4.23. So let omega included into Rn, right, be an open set. Openness is important, crucial, I would say. So then this space of infinitely continuously differentiable function with compact support on omega, right, is dense in LP of omega, right, for any p between 1 and plus infinity. Of course, plus infinity is not included because it will be kind of hardly feasible, right, to approximate an L infinity function by function that are infinitely continuously differentiable with compact support. Okay, so let me just highlight this. So good. So let's go into the proof of this corollary. Okay, so let f of course be an element of LP of omega, right? So what we do first is that we are going to extend f to Rn, right? So because we have some properties about functions being in LP of Rn. So let me just write it. So we extend f, right, to the whole space, right, Rn, right, by setting, the extension is rather trivial, right, not difficult. By being f tilde of x is actually f of x, right, if x is in omega, right, and just 0 if x is not in omega. So this is rather a trivial extension. So f tilde is obviously an element of LP of Rn. Good. Now what we are going to do next is that we are going to break down the problem into, I would say, more manageable pieces, right? So, and for that we do that by approximating the set omega into smaller subset, right, which will allow us to work locally, right, and then at the end we will just piece everything together to obtain the desired result. So so how do we do that? So say what we do is that let me just kind of draw something. So let's say, oops. So let's say well, this is basically, oops, it doesn't look like it. Nice. So this, so let's say this would be, for instance, your open set omega, right? I mean, it's open at the top, right? So what we do is that we are going to approximate omega, right, by balls, right, that for which the boundary is slightly away from the boundary of omega. So what we are going to do is actually, I mean, as I said, we approximate omega with balls, right, for which the boundaries is slightly far away from, I mean, the boundary of omega. So then we just study this, right? Let's use some nice colors. Let's use this color, for instance, right? So what do we do? We just duplicate those. So let me study it and use something. Nope. Yeah, for instance, this color. And then again, I duplicate it. This is just, I mean, duplicate and style it. Kind of the same process. Nope, wanted to duplicate rather. Okay, see, I think we have enough balls already. So what we do, as I said, we approximate the set omega, like with balls, like for which, I mean, the points are, for which the points are kind of, I mean, slightly far away from the boundary of omega. So this would be, for instance, this would be omega 1, for instance, right? So, and then, and so on, you have omega 2 and omega 3. So the second one would be, so this would be omega 2, right? This omega 3, this omega 4, right? And the last one, since I have the right color, so this would be omega 5, for instance. And as I said, we want the boundary, I mean, we want this to be, I mean, slightly far away from, you see, 1 over n. The boundary of those things to be, yeah, say 1 over n. So this is basically the idea. So put omega n. So now I'm going to write what I draw mathematically. So put omega n to be the set of x in omega, right? Such that the norm of x is actually less or equal than n. So we even take it close, right? Less or equal than n. And the distance of x to the complement of omega, right? It's actually greater or equal than 1 over n, right? And this, of course, for every n greater or equal than 1. So observe first that, I mean, this can be rewritten as, this is just to prove that the following set is actually closed. So this is minus infinity n close the preimage of this intersected with distance of these two omega complements. So let me just shift it right of the following interval 1 over n plus infinity. So you have intersection of closed set because the norm is continuous, the distance, like, is actually continuous. Oh, sorry, this is minus 1. So we just write it in color. So for every n actually greater or equal than 1, right, omega n, I mean, is closed, right, unbounded, obviously. It's closed and bounded, so hence compact. by Hein-Borel. Good. So moreover, moreover, our sequence of omega n obviously approximate omega. Then we will have a kind of short proof for that. How do we see that? We obviously know, this inclusion is trivial, right? So the main deal is actually to show that if I have an element x in omega, then that element x lies in one of the omega n. So let's have a short proof, right? Indeed. So let x in omega, right? Since omega is open, that is why I said openness is important. So since omega is open, there exists an integer. I can always find an integer, right? N0 in n, right? Such that the ball centered at x and radius n0, right, is contained into omega, right? So this is always true. But this is just the definition of omega being open. So moreover, as the complement of omega is closed, right, and then another that x is actually into omega, you have that, we are sure that the distance from x to omega complement is actually strictly greater than 0, right? So this means so we can choose n0, right, such that the distance of x to omega complement is greater or equal than 1 over n0, right? And you have that x is an element of omega n0, whence omega is contained into the union of omega n, right? So good. So our sequence of set omega n's, right, which are compact, obviously approximate omega. Okay, now put g to be chi of omega n, right, the indicator function, times f tilde. And then you put also fn to be rho n convoluted with gn. Oh, oops, this was gn, right? Okay, so that rho n is sequence of modifiers once again. So that the support of fn, right, is actually contained. We know already that support of the convolution is contained into the closure of the sum of the support. So this is contained into this. I think we did it already once. So this is contained into this plus omega n, right? Because the support of gn is omega n, right? Definitely. And obviously this is actually contained into omega n. So it follows. This was actually follows by proposition 4.20. I recall that. Follow from proposition 4.20 that Fn, right, is in C infinity C of Rn, right? Because let me just say why. As the sequence of modifiers are actually element of C infinity C of Rn, right? And Gn is in LP log of Rn, right? And then we saw that the LP log of Rn is actually contained into L1 log. Let me just squeeze it. which is contained into L1 log of Rn, right? So On convoluted with Gn, right, is actually in C infinity of Rn moreover moreover the support of this is compact. So this is why Fn is actually in C infinity C of Rn. Okay, so on the other hand, we have the norm of Fn minus F, right, in Lp of omega. Let me precisely the space. This is exactly the norm of Fn minus F tilde in Lp of Rn, right? Because F tilde is just 0, for all the elements that are not in omega. So by triangle inequality, this is actually less or equal than the norm of, I'm just going to rewrite Fn by the convolution product, right, by definition. So this is by triangle inequality less or equal than this times F tilde, right, this is in Lp, norm of Rn, plus the norm of On convoluted with F tilde minus F tilde in Lp of Rn. Like as I said, this is just triangle inequalities. Okay, now this is actually less or equal than the norm of On, right? The norm 1 of On. I'm going a bit fast here. And the norm of Gn minus F tilde, the Lp norm of that, right? Let me just write Lp of Rn, because so far we have two spaces, omega and Rn, plus the norm of On convoluted with F tilde minus F tilde, Lp of Rn. Well, why does this hold? This actually follows by Young's inequality. Right, this was theorem, I don't know, remember 4.15, something like that. Yeah. So apply to this term here. Right, you can put rho n factors. So this is again, let me write it up here, rho n convoluted with Gn minus F tilde. The rho n is actually into L1, right? Rho n is in, this is in L1, right? And this quantity here is actually into Lp. So Young's inequality says that this is less or equal than the norm of On, the L1 norm of On times the Lp norm of Gn minus F tilde. But again, this quantity here is 1, right? This is by definition of modifiers. So this is actually less or equal than the norm of Gn minus F tilde, Lp of Rn, right, plus the norm of On, F tilde minus F tilde in Lp of Rn. Now, this is a very easy exercise. Now observe that that the norm of Gn minus F tilde, minus F tilde in Lp of Rn, right, actually goes to 0 by dominated convergence theorem. So you can check that easily. And the norm of this of rho n convoluted with F tilde minus f tilde in LP of Rn. This also goes to 0, but this is actually by theorem 4.22, right? In fact, because remember that f tilde is actually in LP of Rn, right? Okay, so all the terms on the right hand side go to 0, so we conclude that the norm of Fn minus f LP of omega actually goes to 0. So this ends the proof, right, which was rather really very nice proof, right? Okay, so let's have probably to finish this lecture, let's have corollary, which is something known as the fundamental lemma of calculus of variation. So this is corollary, I think it was 4.24, something like that. Okay, so let omega included into Rn, right, be an open set. Omega should be open, very important. So, and let u be an L1 log of omega, right? So u is actually locally integrable on omega, such that the integral of u f, right, equals to 0 for every f in the space of test function C infinity C of omega. Then we can conclude that u equals 0 almost everywhere on omega. Okay, proof. Okay, let G be in L infinity of Rn. I will explain the main idea of the proof. So just kind of follow for now, right? I will tell you the spirit. So let G be in L infinity of Rn, right? Be a function such that the support of G, right, is the compact set containing to omega. Containing into omega. You agree with me that in that case, if you have a bounded function with compact support, then that function is actually in L1 of Rn. Now, set, you can check that, right? It's a very nice exercise for you. So set Gn to be rho n convoluted with G, right? So we are regularizing the function G. So that Gn is actually C infinity C of omega, right? Provided that n is large enough. So therefore, Gn is obviously in C infinity C of omega. This is what we just proved, right? Because we know that C infinity C of I mean, we saw that if you have if you kind of take the convolution product of a mollifying sequence with an LP function, then the result is a smooth function, right? So therefore, you have by assumption that the integral of u dn equals to 0 for every n, right? And let's call it beta 1. Because remember, by assumption, you have that the integral of u f equals to 0 for every f in the space of test function, right? So gn is actually in the space of test function, so this should hold by assumption. Okay, now since gn actually converges to g in L1 of Rn, right? Because I mean, this is by theorem. We just put refer to the corresponding theorem. This is by theorem 4.22. I mean, this is the theorem we just proved. Right, therefore, I mean, we know that strong convergence in LP implies the existence of a subsequence, right, that converges up to a null set, pointwise up to a null set. So therefore, there exists. Let me just write there exists a subsequence, right, still denoted by, we are not going to relabel the subsequence, so still denoted by gn, right, such that gn converges pointwise to d, right, almost, up to an offset, right, almost everywhere on Rn. We can actually check theorem 4.9, right, for your reference. Okay, I think this was actually on the lecture about probably weak star convergence or weak convergence with topology. Please check out my previous videos on weak topology, weak star topology, reflexive spaces, and superweight spaces. I think we also had a video, right, on separability, reflexivity of LP spaces. Yeah. I think this should be the good reference. Okay, so moreover, we have the norm of dn infinity norm of this, right? In Rn, it's actually less or equal than the norm of dn infinity norm of d in Rn. Right, this is because this integrate to 1, so actually easy to see. So passing to the limit, right, we call it touching beta 1, like that relation. Passing to the limit by, also using dominated convergence theorem. So we obtain that the integral of u d equals 0, and then we call it beta 2. Now, let K, right, be compact set contained in omega. So this is where the proof start now. right? So we establish a result. Now we are going to kind of use what we established to prove our theorem or corollary. So now let K be a compact set in omega, right? So we chose we chose as function G, right? In the previous, what we just saw, we choose as function G the following function. The function that is just kind of indicator function. So this is G equals to the sign of U, right, on K and 0 else, right? This function is obviously in L infinity, right, and has compact support. Right, and then of course we use a convention that that the sign of 0 equals to 0. Okay, so we deduce from beta 2, right? So we deduce from beta 2 that the integral over K, right, of the absolute value of U equals to 0, right? And thus, as I said, this is just a short notation, so always keep that in mind. So this would be integral over K of absolute value of U of X dx. So it's just a short notation. So this equals to 0, and thus we have that U equals to 0 almost everywhere on the compact set K. Now, since this holds for any compact K included into omega, right? So we conclude that U equals 0 almost everywhere on omega, right? Because remember that because omega is open, right, we can actually approximate omega with compact set, as we saw previously. So we can actually conclude and remember that countable union of null set is actually a null set, right? Countable union will be an element of the sigma algebra, and by sigma additivity, it will still be a null set. So this actually ends the proof, and I think we will stop here for this lecture. So thank you once again for watching, and yeah, if you have any question or any you're facing any issues, so please leave your thought in the comment, or you can also reach out to me via email. So we are not alone, so we are here together. So thank you once again, and see you in the next video.